Miss Jody here again with our second video for Energy and Matter class, Thursday mornings 9:30 to noon. So today we're continuing on from what we did last week on learning the characteristics of waves. And so I'll do a little review, but as a reminder, I want you to remember to be taking your notes at home on little half sheets, and then that way we can glue them right in there underneath the label when we get back together. And the best thing would be is on the back, maybe write the title like wave behavior and maybe even your name. And then that way we can glue them on there and we can remember which one goes under which title. Now to try to make it a little more creative, because it looks like we're going to be away from each other for a few weeks, I don't want you to just constantly be doing notes and videos and feel like, oh, it's a lot. So I'm going to try to put a few little fun things in there, just small little crafts and activities. That way you have something to do to make it a little more exciting for me for the journals. And I will be showing you one of the things that I want you to do that goes along with the waves when I review here. Okay, so today is going to be about wave behavior, but it's good for us to look back and remember the world of waves. So when we first started waves, you remember we were talking about wave terminology. And what that means is that we have to understand the world of waves. Like when we talk about waves, what words are we going to be using? Well, first we also have to know what a wave is, and we remember that it's a periodic back and forth motion. It's what we call oscillations, going back and forth and back and forth, and when it's doing that, it's transmitting energy. And so waves are a way of transmitting energy, and these waves will flow through what we call medium. A medium is the substance which a wave transfers its energy. It's what we call propagation. It's propagating the energy down the wave. Now, do note that we've already done this page, so don't be taking notes on this. This is just a review. You've already done this one in your journal at the center the week before we were separated. Okay, so wave, we know it's back and forth oscillations, transmitting energy. It's going through a medium. Now, we will find out later that not all waves need a medium to flow through. Light is one of those specific ones. However, the one that we're going to talk about next, sound, after we're done with this terminology and characteristics and behavior, then we'll need something to flow through. And we always think of medium if we try to illustrate it as water, because think of a water wave, right? So as the water is moving, or as the energy is transferring down through the water molecules, it creates a disturbance, and that's the wave, right? Now, one thing we have to note when it's moving through, propagating, the wave is moving through, then the actual media, and we use the word media when it's plural, meaning more than one of these water molecules. And that's what my little circles will represent, little water molecules. There's a lot of them, so it's media. So these water molecules, they're not going to be displaced in the end. So meaning that this water molecule, once the wave moves through it, he doesn't end up over here. The energy just moves through that vibration. It hits that guy and that one and that one and that one. The vibrations just keep moving through. And then in the end, the wave moves through and it transmits the energy, but not the actual water molecules themselves. And it's good to illustrate this with a little ducky, because the little ducky, if he's on the water, as the water's moving, the waves are moving through, the ducky's just bouncing up and down, right? So he's not actually moving to the other side. He's just simply riding on the wave as it's being the water molecules are being displaced by the energy. And so the energy goes this way, he goes up and down, up and down. So the point is, waves do not transmit matter. So the ducky would be matter, or the water molecule would be matter. They just transmit the energy along that matter there, along the medium. And so there's no net move of the media as a whole. This little water molecule guy is still over here. He didn't float along with it and end up here. The energy just traveled through him. And so in the world of waves, we know that the energy is going to travel through something. Well, most of the waves will travel through something, and we will call them the media, or the medium, the substance. All right, then there's also the wave pulse. The wave pulse is the ripple disturbance that travels down the wave. So this disturbance of the water molecules going back and forth, being disturbed by this energy trying to flow through them, that's what we call the wave pulse. And you remember from our last video, there's the two main types of waves. We've got the transverse waves and the longitudinal waves. And so the transverse waves are waves that when you move up and down, so say I'm standing here and I'm holding this jump rope and I'm moving the jump rope up and down, my wave will propagate like this. And it will propagate in this direction. This is what we call 90 degrees when we look at angles. So I'm moving it up and down, yet the wave is going this way. So a transverse wave will be a wave that when you move something up and down, it'll flow in this 90 degree. And then the longitudinal waves, they're going to be a little different. I'm going to be putting the energy in here with my little arrow, and it's kind of like my little slinky here, if you remember. And as the energy goes in, it's going to squeeze and then let out, and then squeeze and let out, and then squeeze and let out as it's moving down. These little arrows are just representing squeezing and letting out, squeezing and letting out. And so the longitudinal waves, they will flow in the same direction of the energy that's actually put into the system there. Where this one, the energy is going up and down and it makes it flow that direction. So when we know wave terminology, it helps us, right? It helps us understand the world of waves. The other thing we had to learn in our last video is the characteristics of waves, meaning like how would we describe a wave? So if somebody has characteristics, like the characteristics of Miss Jody, you might say are a little quirky, or maybe you'll say I'm fun, or maybe you'll say I'm cranky, who knows, right? So there's certain characteristics. So with the characteristics of waves, we talk about 4 main characteristics of waves. Remember last time in our video, wavelength, amplitude, frequency, and speed. So I wrote them in the 4 because every time we talk about a certain wave, whether it's going to be sound or light or whatever, we're going to have to look at those 4 things for each one of them. And so wavelength is just the length of the wave. Remember, like the transverse wave, it's from crest to crest or from trough to trough. How long is the wave? Some waves are very, very long waves, and you could measure them in meters because they're so long. And but some wavelengths are really small, and you would have to go really into a small scale, really down to micro and all that to measure these waves, because they're just the in between the crest and crest is like little tiny waves. And so we have all different wavelengths. And with the longitudinal waves, it's similar, but thinking of it as the little slinky, you have to remember it's from compression to compression or rarefaction to rarefaction. Now, compression to compression is squeeze to squeeze, and rarefaction to rarefaction is spread out to spread out. And so as it's moving through like the slinky, and we illustrated this last time, you remember, with my little thing of copper wire, and I stuck it back in this coil, or this little holder, so it could stay coiled. But you remember I had this and I was doing this like in and out. See how it's doing that? And so as I'm putting the energy in on one side, then it would go certain places, it would squeeze in and then out, and then in and then out. And as it would do that, the energy would move down in a pulse that way, right? And so from compression to compression, so squeeze to squeeze or spread out to spread out, that'd be one wavelength. So we'd be able to measure how long the waves are. Now, when we measure our wavelength, we use this little guy, the lambda, if you remember, for our equations. And then we also measure it in meters. Then we talked about amplitude. Remember amplitude? That's how big the wave, how much the distance of it being displaced. And so if I have a wavelength and I put a lot of energy in it, it might fly up really high as it's being displaced. So when we displace the media, so this is like, say this is water, and I throw a big giant rock in it, and then the waves get really, really big. I've displaced them really a lot, right? By that energy that moved through the water since the rock was thrown into it. And that would be, they would have a higher amplitude. Amplitude is the maximum distance the particles are displaced by the wave. So how big it gets there. And so if I only disturb it a little bit, I might get only a little amplitude. And so when we look at that, it helps us understand the world of amplitude, and that's measured in meters in our little a there. And then if you remember frequency is the number of waves. Now, it's not the full crest to crest or trough to trough, but it's a crest and a trough, a full wave that pass a given point per unit of time. And so I would take my little wave here and I'd figure out how many waves pass this particular point here to figure out its frequency. And you know, when we talk about frequency, when I always talk about things like waves, like really waves with really long wavelengths, if it's really, really long, then it's really not gonna pass that point that much. But the shorter the wavelength, if the wavelengths only get a little shorter there, then it might be able to pass this point, like 1, 2, 3 times during this 1 second. And so a frequency is all about how many waves will pass that certain point in 1 second. And that's measured in the hertz. In the hertz, we can always see as how many per second there, waves per second. So if I have a wave that is really very small wavelength, that means like if, let me just draw it in here like this guy, his wavelengths are like this. And he's really small, the length of how far apart his waves are, so small. And I measure him the same amount of time as I measure this guy. This guy only passed this line 1, 2, 3 times, right? This guy, he would, in that same amount of time, he'd pass that line 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. He would have a higher frequency. And so this is why we talk about, when we talk about these waves that are hitting us, like from the sunlight and from any of the electromagnetic spectrum, when we have something like radio waves, and those are going to be really big waves, and that are traveling, and that's how we send our sound through the radio. And so when those waves hit us, they're invisible. We can't see them, but they are hitting us. And so when they do hit us, they're so long in wavelength that they only hit us a little bit each time. But if you get in the presence of a really short wave, like an X-ray or a gamma wave, then you're going to not want to be in the presence of it, because it's going to be so short that in 1 second it's going to hit you boom, 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 so many times. And that'll be too much energy for your body to absorb and your cells. And so it wouldn't be good to be in the presence of things that are really have really short wavelengths and real high frequencies. Going to hit you a lot. And so that frequency is all about how many waves per the amount of time. And then also speed, you remember that? That was the rate at which a wave travels. And we talk about waves are traveling at different speeds, right? And so we can figure out the speed of a wave and figure out the distance and how long it took to get there. Distance divided by time. Now speed, the rate at which it's traveling, is just a scalar observation. That means it doesn't have direction. But if we're going to say the wave was going this direction, then we have to calculate it as a velocity, adding that direction. So v is equal to distance over time. And so you remember that. Now, don't worry. These two were just the review pages. These weren't ones you were supposed to do. We've already done them. But we have one today that we're going to be doing. And this was just a review so we could remember that. Now, like I said, with the activities that I want to do for you, a few of them that I'm going to do just so you have some creativity at home, this is one of the half sheets that's going to be part of your PDF that I send you today. That will be something that will be printed out. I saved this along with the next diagram on one sheet, so that way you could just print one sheet of paper and that you wouldn't have too much printing out and wasting of ink. So this one I thought would just be a fun way for us to do some waves, some art with some waves, and specifically because we're going to be using water waves as an example today. So I have Catherine in the other classroom. She's here with me today at the center. And she's working on coloring this really beautifully with some markers, and then she's going to bring it over to me at the end of the video, and I'm going to add some water to it just to kind of represent the waves of water, since we'll be talking about that, and then we'll see what it ends up looking like in the end with all the markers blending all over together on the pattern of the waves, okay? So I'll be sending that to you for you to work on at home, and that'll be fun, and save that because we'll glue it right in the journal, right? Now today's page that we have to go over is continuing this idea of waves. So we already said the waves terminology. What are words that will be going along with waves? And then we said wave characteristics. What are the characteristics of waves? What can we see about waves? And then now we want to figure out what's the wave behavior. How do waves behave in certain situations? And so again, we have 4 areas for wave behavior. And that just helps us keep it all organized in our mind. And so with that, we have the reflection, refraction, diffraction, and interference. And so we're going to look at all 4 of them, and then I've also given you the diagram. Each one of these diagrams represents those 4 things in order, so that while you're doing this lesson, you can have that piece printed out, and you can use your colored pencils or markers to follow along with me. All right, so the first way that the wave is going to behave is the process we call reflection. So reflection is a change in the course of a wave as a result of a collision with an object or a boundary. So if a wave collides with something, it can be an object or it can be an invisible boundary into a new substance, then the wave's going to behave a certain way. Okay, and so with this behavior, let me show you what that means, okay? So I'm gonna, with my highlighter here on this top one, which is the reflection one, I'm gonna just draw some little lines with my highlighter. And that's going to be my wave as it's flowing, okay? And I'm going to use my blue to represent in between, because what we want to represent with this wave is picture the wave motion that we talked about as it's moving along. I'm going to draw this, see this side to side, side to side, side to side. I'm trying to represent that transverse wave there. And so or whichever wave, it could be either. I'm representing this back and forth oscillation of the wave. So as the wave is coming in and it's rippling, ripple, 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 and it's all going in a certain direction, and then all of a sudden it hits this boundary and it can't move anymore, right? So it's going to have to go through that process we call reflection. It can't move through this boundary. Let's say this boundary is so like a wall, it can't move through. So say this is either light trying to come through and this is a mirror, or let's say this is a water wave trying to come through and it hits the wall, then it's going to have to go through a process, a change. And so what it's going to do is it's going to reflect. And so it's going to go this direction. Now, when it goes this direction, we can use this understanding to figure out like the pattern of which way it's going to go and the angles. And so let me draw it going this way now. So we got it going this way, and it got reflected off. Now the wave that's coming in, we call that the wave of incident, or ray if you're talking about light. Okay, so the wave of incident. So just think of it this way: when the waves come in, it hits. There's an incident. Like if you think of something like on the playground and two people have an incident, it's because they've done, maybe they've knocked into each other or something like that. So we use the word incident. Okay, so in it comes and it hits. There's the incident. And then it reflects back out. And so this will be the incident wave, and this will be the reflected wave. And in the middle, what we do is we draw this invisible line. We're going to call this invisible line the normal. And this is just so we can track the angles of how this works. And so we will put the normal there. And then what we can do is we can draw out or we can use some letters to help us understand these angles. So I'll say this is my wave coming in. I'm going to mark it as A. Okay, and then as I mark it as A, as it comes in, it's gonna hit. So I'm gonna mark that hitting spot as B. So as it hits, then my invisible line here, my normal, I'm gonna mark that as N. So this way I can do a little math calculation, and I can figure out the angle between A, B to N. So if my angle is A, B, N, then I can use my tools for calculating angles, and I would figure out that this is a 45-degree angle. Now I'm going to use a different color just to illustrate that angle there. So from A to B, B to N, there's my angle. And I'm going to make that orange, okay? And then the next one, I'll use a different color, and this will be my next set of angles. So I've found the angle of the incident ray, the angle of incidence. That's what we would call it. And then I look at my next wave as it's moving out, and I'd have to figure out this angle. And this would be called the angle of reflection. And so I would say, okay, I would start with which direction? I would start N to B to, I'd have to label this one as C. So N to B to C, and I'm going to write that. So from N to B to C would be another 45-degree angle. And so my 45-degree angle for N to C, you see, from N to B to C. And that would be my second angle, the angle of reflection. Now, when we look at something like that, we realize that these match, right? And so what happens is we have been able to put together a law because it always matches. And it wasn't us, and of course it was scientists way before us who figured out the law of reflection. So each one of these behaviors, I also have put like a rule that goes with them, and I circled it. This rule is this: the law of reflection states that the angle of incidence equals the angle of reflection. So no matter what, when you're actually reflecting, you can always find that the angles will match each other. And these two, if you add 45 and 45, will create the 90-degree angle. Now, let me see if I can put a color here and see if that works. let's try this red marker. You know, with the markers here at Science Center, you never know if they work. So here's the big angle of the two. That big angle would be 90 degrees. It'd be 45 plus 45. And so it's neat that there's a certain law that governs how the reflection works. All right, the next one is refraction. Refraction is the bending of the path of a wave as a result of a change in the wave's speed. And so what happens is when the waves are coming, they're going to, as they're moving along, they're going to be at a constant speed in the particular media that they're moving through. But if they come along a boundary of either a different media or a media that changes in a way like temperature or something, then there's going to be a bending. Okay, so I'm going to illustrate this in the second one. And so say my wave is moving, and let's say he's moving really, really fast. And as he's moving really fast, the wave, and he's in this particular medium, and I'm doing kind of trying to do like a dark blue for this, because this is illustrated really well in how the waves move in water. And so if you're in really deep water, waves can move a lot faster in deep water, and it's a lot cooler down there than in the shallow parts of the water. And so say my wave is moving in the deep water. So as it's moving in the deep water, we have it moving really fast, and then once it hits this new area of water, it can be the same thing. They can both be water, but there's still a boundary. This boundary means something changes in the media. This is really deep water, and then the new media is going to be shallow water, which is going to change the temperature, of course, because shallow water is going to be warmer than the deeper water. And so the wave has got to move through it differently, and once it hits that boundary. And so as it moves through, it's going to now be moving in, and it's going to go a little slower, right, in the shallow water. And so I'm going to represent that with my blue coloring. I guess I should do it this way so it looks more wave-like. Okay, so as it's moving through, we have the change because of that boundary, right? And so if you put this, like say we put this in a little ripple tank, the refraction of the water waves could be illustrated in a ripple tank. Like if you know what a ripple tank is, where they put water, and I'll show you a picture from the book, you'll see. But they put water in it, and then they disturb the water and see how the waves move, okay? So if we put it in a ripple tank, we'd be able to see this. And we could insert something that would kind of change the way of the movement. And it would move the wave along depending on which different media that we could put it in. So then after crossing a boundary, the wave would slow down, causing them to change direction towards the shallow water. And so if we created that two different things in the wave tank, then it would hit that boundary, and then it would have to move. Now what's neat about it is that there's a rule with this also. So refracted waves, the ones that are going to be bending, they're going to always bend towards the medium that slows them down. So as he's going in this wave, you know, he's moving in this direction, and he hits right here first, right? Because the whole rest of the wave is coming along. And then he hits something that's going to slow him down, so he's going to slide this way. So you've seen this like with cars as they're driving, and if they hit a certain point and they'll slide a certain way. It's the same sort of thing. We have the wave coming in, and he's going really fast, but he hits that boundary, and it's going to slow him down a little bit. And he's going to bend toward the medium that slows him down. And then we will see a change in the wave, right? And so the next one that we have is what we call diffraction. Now, diffraction is the spreading out of a wave after it passes through a narrow opening. Okay, so what happens is in this diagram, if we have a little narrow opening and we say we have this wave coming in, and he's coming in pretty straight, right? And then he gets through, there's a boundary with a little opening there. So when he goes through that opening, now the opening has to be kind of small to make a big difference. And so as he tries to move through, instead of being nice and straight, he's going to go through the process of diffracting. Half of it will come as the wave moves through, it'll start to bend through that hole, and it will change it a little bit as it's moving through. And that's that process we call diffraction, the spreading out of a wave after it passes through a narrow opening. Now, the reason narrow is important is that when you have a big opening, you're not going to see the same thing as what a narrow opening is. So diffraction causes the wave to spread out evenly when the opening is roughly equal to one wavelength. So if the opening is small enough that it's only the distance of one wavelength, and you remember what a wavelength would look like, it would be like from here to here, okay? So these are my ripples. Just picture them like this, okay? And so if my opening is only the width of one wavelength, there's one wavelength right here. So if it's only that amount of width, then we have them to be able to spread out nice and evenly. But see, if you open the opening a bigger, then you're not going to have that same thing. So if you have very little, or if it's big, very little diffraction occurs if the opening is many times larger than the wavelength. So if this opening is really, really big, you're not going to see that same amount of diffraction, this kind of spreading out instead of going straight in, okay? If the opening is much smaller than one wavelength, no part of the wave will penetrate the gap. So if we squeeze the gap and make it too small, that it's not even the length of a wavelength, then nothing will go through. If we had a really small little pinhole, okay? So there's little ways, so let's note that so we don't forget the wavelength. So if we have a bigger gap, right, there's not going to be as much of the very little of the diffraction. So very little diffraction, but if we have this nice wavelength, then we'll have a good amount. That's the middle guy. So if it's too big, you're gonna have very little diffraction. If it's just the right wavelength, it's gonna be spreading out evenly. So that's what this one will be, nice and evenly. And then if it's really too small, then it's not gonna go through, it's not gonna get in at all. So we'll have nothing. We'll put not at all because it will be too small to get through. And so the wave will be diffracted depending on the size of the little hole it's going through. Okay, so that's one rule we have to remember with diffraction. So as a reminder, we've got reflection that's going to be bouncing off and having the equal angles. And then we've got the fact of refraction, which is going to be bending. And this is all going to be about the medium. So I'll put that all about the media it is going through. So if it changes to a different either temperature of the media or a different degree or even a different substance, it's going to change the speed, and it's going to have to change depending on what it's going through. And then this one, as it's trying to go through the hole, if it's too big, you're not going to have much of this happening, this spreading out, sort of passing through the hole. You're just going to have just regular wave movement. And then, but if it's just the right size, it's going to spread out nice and evenly. If it's too small, not at all. Okay. And then our last one is what we call interference. Now, interference is the reinforcement or even cancellation that occurs when two or more waves meet. So what happens is waves, they can interfere with each other. It can be constructive interference. That means they interfere and knock into each other, but because it's a constructive way, they will help each other become more intense. And then, but if they interfere destructively, then it will cancel them out. Now let me show you what that means in this diagram. So in this diagram, you'll see, and let me use two different colors that are kind of hopefully easy to see. So let's use the orange, and then I'll use the yellow highlighter. Okay, so if you look at this diagram, and it's kind of dark, but on your own diagram, hopefully you can see that there's going to be two openings. Now, in this one, we had just one opening for the wave to get in. This one's going to illustrate two openings, okay? So this is similar to what's happening here in the diffraction side of things. But this I'm going to have this opening right here, and it's going to let some in there of the wave. And then this opening is going to let the wave in here. Okay, now these are both still the same wave. It's just we have to illustrate them with two colors so we can keep track of who's going where through which hole. Okay, so let's picture that to be the same thing coming through. I'm just going to draw this like this, my wave. Okay, I'm just using the color of orange and yellow to separate the wave getting through the two different dots. So the wave that got through this dot, he's going to start coming through this little, you can barely see it. And as he's doing it, he's going to be creating that little wave pattern. So I'm going to try, this is going to be a little difficult here to illustrate, but you see I've got the first little black part here. I made him orange. And then I have my orange guy going again and again and again and again, and it keeps moving out. And I'm trying to not get confused on these lines here because it starts to get really wacky. As he's moving through the hole, he's doing like this one right here. And so he keeps moving through, and my eyes start to get blurred after a while. Okay, and then I eventually won't be able to keep track of my lines, but you picture what I'm saying, right? And so as my part of the wave is moving through that hole, he's spreading out. And then how the wave is moving through this hole, he starts spreading out too. He does his little loops. And so he starts looping out and looping out and looping out and looping out, going through that hole. And so as he's doing that, he's spreading out too in the same way that the orange guy was. Now what happens is these different lines, you can see they're dark colored and they're light colored. What they're representing is the bumps, okay? So like we talked about before with the waves, we've got this, the crest and the trowel, the crest and the trowel. And so with the dark color, they're representing the crest, and with the light color, they're representing the trowel, or vice versa. So when you have the first set of wave, it's dark, okay, and he comes out, and then the next lighter one, so that would be the dark one, and the lighter would be going the other direction, and the dark one, then the light one, the dark one, the light one. And so they're representing these bubbles of these waves coming out. Now what ends up happening is, depending on the waves that were part of this orange group over here and the waves that were part of the yellow here, there's times when they're going to cross over. And when they cross over, if they cross over in a way where both the crest and the crest touch, and so let's say that's one particular wave, and then the other wave as he's crossing over, and his crest and his trowel meet. So his crest up here, so say these two crests of one of the orange and one of the yellow guy, if they meet, then they're going to work together, both crest and both trowel. So I'm going to just do this as a yellow, as an orange, and then this one as the yellow. And so the crest to the crest, when they meet, that's going to actually be what we call constructive. See, crest to crest, that's going to be constructive. And so they will come together, and because they're both going in the same direction on when they cross over, and they're both the same crest part, then they will come together and increase this, and so they will be kind of making it stronger because of that crossover of the crest to crest. But what happens if you have, when they touch, and maybe you have a wave like this and another wave like this? Terrible drawing here, but let's say the crest of this wave and the trowel of this wave come together. If they come together, that would be destructive. So they will cancel each other out. And so in certain areas of the wave, if they come together, they can make themselves better and stronger because they take on come together and share that intensity there. But then if they are going the opposite way, that's the trowel of the wave, and this is the crest of the wave, then they're going to cancel each other out. And that will be, instead of constructive, this will be destructive. Interference. And so as it's moving through, we can see the world of interfering. So waves can start interfering with each other. And it's kind of cool. It'll make a really awesome pattern. And then in the end, you'll have different things coming out at the end, depending on the intensity of the constructive interference versus the destructive interference of canceling it out. So I'll try to put a video in there with these that show these particular properties for you to, or behaviors so you can see them for yourself. Maybe this one in water. This is a good illustration of water. Light also does this type of interference. So light does it and creates a weird pattern, and so does water waves. And so and sound works in this. So you can have constructive interference or you can have destructive interference with sound. So all of these cool things, they obviously show us how waves are going to be behaving, and then we can put that together as we're studying waves. So we'll know how the characteristics of the waves, the way the waves behave, we know the terminology, and then our next video will be moving into sound, which is one of the waves, and we'll be able to say, oh yeah, waves, sound. Does it reflect? Does it refract? Does it diffract? Does it interfere? Because we'll know the behaviors of waves. And then we'll also be able to look at the wave characteristics of sound, and we'll say, okay, what are the wavelengths of sound, and what are the amplitudes of sound, and what does that go with, and what are the frequencies of sound, and what's the speed of sound. So we'll be able to use all these things in every single of the waves that we talk about. Now, finishing up, remember I told you that I was going to have this little art thing just to kind of make it fun. And so Catherine has been so generous to color this for me while I was making my video, and she did a great job, didn't she, making all different kinds of cool patterns there. And then all I'm going to do is I'm just going to spray a little water on it, because now if you don't have a spray bottle, you could just drip some water on it. You just use your fingers, right? Just to see if we can get some cool wavy patterns with putting a little bit of water onto the paper. We'll see what ends up happening. I'm not going to put too much, but I want to see what happens with the colors as they kind of bleed together. And we'll see in the end what this looks like. I think that would be kind of cool to make it a little watery, bubbly pattern. And then when I put it into the journal, it will remind us of the waves, and using the waves of water to illustrate the wave characteristics and the wave behavior. Okay, so it's kind of blending together, making a cool pattern, and I'll let that dry, and in the next video I'll show you what it ended up looking like. And so that will go into our journal next to the wave characteristics and help us understand the wave behavior. Okay, I'll see you next time.